it's very nice to follow Jonathan because he introduced some of the important ideas that I want to talk about. But so I'm going to be telling you some general things. Then I'm going to be telling you a little bit about work that we have done. And the work that we have done has been in collaboration with, it was done when all these people were at Northwestern, but Juan is now at Imperial College London. He's an assistant professor there. Matt Perridge is now doing a postdoc with Kanaka Rajan in New York. Rahid is doing a postdoc with a group of Aaron Batista, and Lee Miller is my very excellent colleague who runs a monkey lab, and all the experimental data that we analyze come from him and his people. So this is the bulk of what I'm going to tell you, and at the very end I will make some comments about some ideas on how to use novel, very sort of new machine learning techniques that allow us to do something that we had not been able to do otherwise. So let me start with telling you a very simple motor task. So I'm going to be a little bit different from Jonathan this way. I'm going to start by telling you a task and telling you the data and analyzing that particular data set. So this is a task which is a little bit like the pendulum problem for physicists. It's a task that everybody who works on motor control uses. It's like the typical task, and it's what is called a center-out task. So essentially, there is a circle with 8 targets on the circle, and there is a circle at the center, and the monkey is moving a manipulandum, or you can do it with humans also, and you put the cursor at the center, and then one of the 8 targets gets very briefly illuminated, and it goes off, and you have to wait for a go signal, and when the go signal comes in, you're supposed to move the manipulandum and capture the target that was indicated by the flash, and then you get a reward. So this is the sequence. You get the target, you get a go signal, you capture the target, you get a reward, and monkeys get very, very, very good at doing this. And while the monkeys are executing this task, we are recording from neurons, and this is the type of data that Jonathan showed you before. We use multi-electrode arrays that are implanted in the primary motor cortex, which is an area of your brain that is kind of like where your earphones go, sort of from ear to ear. It's a band that is, of course, using contralateral control. And here I'm showing you, this is about 20 seconds of data. This is a case where we recorded of the order of 80 neurons. It's a raster plot. Every little dot is a spike. And this is exactly the kind of data that Jonathan was showing you before. And the question is, how do we describe this data? And I'm sorry that Ken is not here, because Ken Harris is giving the last talk, and I am going to make some comments that connected to his talk, so I was hoping he would be here. But so how do we organize this data? We organize this data as population activity. So imagine that I was able to record all the neurons in primary motor cortex that are in the arm area and involved in this particular task. That would be of the order of 10 to the 6. That would be of the order of 1 million neurons. So imagine for a moment that I could record all of them. This is the concept that Ken will talk about as n infinity, or n going to infinity. It doesn't mean that you have an infinite number of neurons, but it will mean that you can actually record all the neurons in the area that are relevant or modulated by the task that you are trying to study. So at every time t, I measure all my neurons, from neuron 1 to neuron 2 to neuron 10 to the 6, and then I do the same at time t minus 1, at time t plus capital T. So capital T is the duration of the task. So again, it's this idea that you bin time, and what you're doing is you're measuring the number of spikes that each one of these neurons emits in each one of these time bins. And so you get a matrix that has as many rows as the number of neurons and as many columns as time bins you have during the duration of your experiment. For instance, that could be one reach, or could be a monkey executing many reaches, and you're recording over a long sequence of reaches to different directions. The data is taken by this the data that I will be showing you is taken by these multi-electrode arrays. These are about They are about 4 millimeters by 4 millimeters, so there's about 400 microns between electrodes, and it's a 10 by 10 electrode array. So it allows us to record from the order of 100 neurons. And so now what we are subsampling. I'm not recording from the infinite number of neurons in the sense of all the neurons that were modulated by the task, but I'm recording from the order of 100 neurons in the case of multi-electrode arrays, maybe 1,000 to 10,000 neurons if you use neuropixels, but it's a very strong subsampling given that I have of the order of 1 million neurons participating in the task. So this dimension D is the dimensionality of the data that I can start with. It's never n infinity because we never have access to all the neurons that are being co-modulated by the task. It's what people call the ambient dimension. It's essentially the dimension not of the real neural space, but of the empirical neural space that you have access to, given whatever is your measuring device. And so what you want to do is something like this, and you want to do this kind of prediction that Jonathan also talked about. So for instance, this is a yellow target appearing, and then I measure activity, let's say 300 milliseconds later during the Gauss signal, and this is the response to the reach corresponding to the red target, to the blue target. And the name of the game is, if I just gave you the spiking activity, this vector of spiking activities for every one of those time beings, would you be able to tell to which target the monkey is going to move before the monkey actually executes the movement? So this is a code for the target. Can you actually unravel that code? Can you decode that neural signal? Well, if you use a very simple you'll see me sitting down every now and then. It's because my hip is killing me. So every now and then I can't stand up anymore. So if you take a very simple point of view and you said, I'm just going to pick 3 neurons, so let me go back and said, I'm going to pick, this neuron, which is in red here, another neuron that is in red here, and another one, which I don't quite see, but I pick 3 neurons at random. And so I make a 3-dimensional plot, which is the activity of these neurons, number 78, number 46, number 70. So every time there is a reach, every one of these reaches is a point in this 3-dimensional space. I put the point in this 3-dimensional space, and then I color the points afterwards according to which was the target that reach belonged to. Well, you can look at this, and there isn't much of a structure there. It's not obvious that there will be a structure to it. But actually, there is a structure, and we're going to try to understand it from the point of view of the existence of manifolds. So what is it that we're doing, really? What we're doing is we have this network, which has this n infinity number of neurons, and we are actually putting some electrodes here, electrode in neuron 1, neuron 2, neuron 3, and we don't know anything about these neurons, really, with this particular type of electrode array. It's just pushed in, and you don't know exactly what type of neuron you're recording from, although I think you are going to talk a little bit about that, right? About the interplay between manifolds and types of neurons. But at this point, we are very naive about that, and we ignore the distinction between neurons. We don't know even if they are excitatory or inhibitory. We just know that neuron 1 makes these spikes, neuron 2 makes these spikes, and neuron 3 makes these spikes. This is what we are recording. The very interesting observation that happens, which was made by a lot of smart people who work on this problem before we got into it, is that if you go to this 3-dimensional space, and the axes are activity of neuron 1, activity of neuron 2, and neuron 3, and you follow the activity now as a function of time, you see the dynamics of that neural activity is not exploring the full 3-dimensional space. It's exploring a low-dimensional manifold that is embedded in that 3-dimensional space. So the 3-dimensional space in this case would be the ambient space. 3 would be the ambient dimension, the number of neurons that you're recording from. But there is a restriction of the dynamics of the neural network to a low-dimensional object, which is this cursed word manifold, that you should not use, you should not invoke it in vain or something like that, so if you're going to be religious about it. But I actually, I am very, very proud that I work mostly with experimentalists, and now we have these lab meetings and everybody talks about manifolds. So I think it's one of my greatest achievements in a neuroscience department where everybody except me is an experimentalist, that people discuss manifolds like they discuss electrodes and things like that, so. Say it again? Did I? Hausdorff space. Well, that's a bit more ambitious, but manifolds is already quite an achievement. Well, so what this suggests is that it was very, very stupid to try to look at things in the space that is spanned by this axis, N1, N2, N3, because this is moving in a surface that is not defined by N1, N2, and N3, but by particular combinations of these activities, which is what we call the neural modes. Now, this, of course, had been observed before. This here is the very naive picture that I showed you earlier, where I'm just plotting the discharge of 3 arbitrary neurons as a function of each other. And this is work that actually Manish was part of many years ago. Now, I think this was premotor, right? This is recorded in premotor cortex, not in M1. And what they did is use factors analysis to try to do a dimensionality reduction, an unsupervised dimensionality reduction, like Jonathan explained. And then again, what you see here in this case is that these points in this 3-dimensional space spanned by 3 different neural modes allows you to cluster the data very beautifully. And it's not only that there is a cluster per target, but if you look at it, the clusters themselves are organized in the same topology as the targets are organized in real space. So in some sense, this representation, which is not a dynamics representation, here is 1 point per reach, like the one I was showing you in my very naive picture before, shows you the structure. Both premotor cortex and primary motor cortex are representing the spatial structure of the task that you are about to execute in their neural code. Now, the more modern way to think about it, and also is something that Jonathan alluded to, is to think of these low-dimensional variables that would allow you to describe this low-dimensional manifold as latent variables that are actually a generative model. These are like the X's in Jonathan's talk. So if I can think of N1, N2, N3, but I can also think of a 2-dimensional surface, like the one I just showed you, generated by 2 simple vectors, a vector U1 and a vector U2. U1 is 3-dimensional, U2 is also 3-dimensional. And if you look not at the activity of the neurons, but at the activity of these neural modes as a function of time, linear combinations of the neural modes allow you to reconstruct the neural activity, even in a simple linear model. So instead of thinking of the neurons as the building blocks of the activity that I observe, I can think of the latent variables as the building blocks. I can think if I have a description of this low-dimensional space, and I understand what is the basis in that low-dimensional space, even if it's not unique, but it doesn't matter. As long as it spans the appropriate low-dimensional space, if I understand how these latent variables are evolving as a function of time, I can then very easily reconstruct the way in which the neurons should fire. I can get, in the language that Jonathan was using, this would be my P of X, and this would be my P of Y given X. So this is how the latent variables are evolving on time, and this is how the observable variables, which are the firing rates, and actually what you get, of course, it's a continuum to continuum model, you will get firing rates as a function of time. If you want to instantiate spikes, you will have to put a Poisson model, a Poisson dice to generate number of spikes in each one of the bins to put actually the little dots as opposed to draw a continuous firing rate as a function of time. The very interesting thing is that this population dynamics is consistently, and I'll show you several examples next, is very consistently confined to these low-dimensional manifolds, which are embedded in the high-dimensional, in the empirical neural space, in the ambient space. And one of the big things that we need to discuss is whether these dynamics occur in a manifold that is flat, like this, so I can find it using a linear method for dimensionality reduction. In that case, I can find 2 modes, like U1 and U2, as I showed you in the previous slide, that are sufficient to describe the whole flat subspace, right? They provide the basis for the whole subspace, or whether the dynamics is confined to a manifold that is low-dimensional but not flat, is curved, like this is a 2-dimensional manifold, and this is the same 2-dimensional manifold, but it's not flat, right? So now if I want to put a basis here, there is not one basis that will span everything, but it's just a basis whose coordinates or change as you move along the manifold. So this is one of the big things that we need to discuss, is whether we can use a linear or whether we do a non-linear method for finding the description of this manifold. And I want to use a picture, a very nice picture that Serjan did I say that? Surgeon, presented at a workshop that Matt Perich and Juan Gallego organized at the Computational Neuroscience meeting in Barcelona about a year ago, which is this idea of how are these manifolds embedded in the space. So, and it's related to things that Ila Fitte discussed at the same workshop. So this is a one-dimensional manifold, right? It's a string. I can go around that. The intrinsic dimensionality of this manifold is 1. But if I wanted to embed it in a flat space, I need at least 2 dimensions, right? I can put it on the table, and I need a 2-dimensional. And this 2-dimensional flat space could be itself embedded in a 100-dimensional space of neural firing rates. So I have an intrinsic dimensionality of the manifold, and then I have a flat dimensionality, which is like the minimum subspace, the minimum flat subspace that can include this. So now, of course, I could, I can put it on the table and I can wiggle it around as much as I want, and it's still 2 dimensions in flat and 1 dimension intrinsic. But now imagine that I do something like this. I pull it up like that. I pull it away from the table. This is still a 1-dimensional intrinsic manifold, not the way I'm doing it, but like that. But now the flat dimension in which it's embedded is no longer 2, it's 3. And of course, I could do this, and it would still be 3. But imagine that this is embedded in a 100-dimensional space. So I could put the second wiggle that deviates from the plane in any of the other n-3 possible dimensions. So now the flat dimension keeps on increasing, although the intrinsic dimension keeps on being 1. And this is, I think, the purpose of this beautiful picture that Shodan had shown, that you can have this space, PC1, PC2, PC3. The intrinsic dimension is 1, but the embedding dimension, which is what I'm calling the flat dimension, is 2. But if you make it wiggle like that, you will need a flat dimension which is larger than 2. Or if your intrinsic manifold, if your manifold is the surface of this sphere, the intrinsic dimension is 2, but the embedding flat space, minimum flat space in which I can embed it, has dimension 3. So there is a difference that we need to keep in mind, and you really need to keep in mind when you hear Ken's talk at the end. There is a difference between flat dimensions and intrinsic dimensions. And if you compute the flat dimensions, you learn a lot, but what you learn in some sense is an upper bound to the true intrinsic dimension of the manifold, right? The flat manifold is like the minimum subspace in which you can embed the true manifold with its true intrinsic dimension, which is actually much harder to find than the flat dimension. So this is the famous paper that triggered this controversy. At that time, I was very happy not to be in Twitter, so that all this didn't mean anything to me, although people were arguing very, very vividly, very intensely about this. I mean, it's nice that people would care so deeply about something like that. What's the correct definition of a manifold? But our main point in this paper that we wrote, actually, thanks to a meeting that Per Roland organized in Copenhagen at that time to discuss how the brain works. And then there was an issue of a neuron where we were invited to write these perspectives, and we wrote about that, about the role of these neural manifolds and latent dynamics for the control of movement. And even at that time, in that paper, which is 2017, we listed a lot of places where these manifolds are observed, although we were mostly interested in using them for understanding motor control. They are found in frontal and prefrontal and parietal areas, in sensory areas such as visual, auditory, and olfactory cortices. So our idea was that these are really the building blocks that we should look into in order to try to understand how the brain processes information, how the brain uses neural activity in order to compute, as opposed to looking at a population thinking that every neuron is the correct independent object to look at. And this is a list from 2017, and if you look more recently, there is a lot of really beautiful papers, as some of the work you'll hear about here. So you'll be here about this work from Davina, and you'll be here about this work, obviously. And okay, so you'll hear about many of these very interesting and more recent ideas. So what I want to tell you is mostly that a lot is gained by staying flat, that there is an unreasonable effectiveness of linear methods in trying to understand these manifolds. And in this sense, I deviate a little bit from Jonathan's philosophy, because he tried to explain to you the importance of being nonlinear, both in modeling the P of x, which was the probability distribution of the latent variables in the manifold, and the P of y given x, which is the generative model from which you would get spikes from that latent activity. So I always tell my students in particular, let's first go linear and see how far we can go. It turns out that although I've been working for so many years, I always find new things to learn about linear algebra, which is to me very, very surprising that there are still things about linear algebra that I don't quite know. And it's interesting to see how far you can go, because then where you fail perhaps gives you an idea of what kind of nonlinearities you need to introduce. Because the moment you say, I abandon the linear world and I'm going to go nonlinear, is such a vast possibility of models. There is no way to explore them all, and you have to have some intuition about what kind of nonlinear model or what kind of nonlinear approach you're going to use. And so that will require some intuition about how the linear models fail. So let me walk you through what we now, referring to our own work, things that we have been doing. And so one of the things that we observe is that when monkeys do this centered out task, they have a very, very remarkable behavioral stability. So this is a monkey who has been doing this task for almost 2 years. So this is days between sessions from 1 to 800. So this is 2 years of data. I mean, the monkey doesn't come to the lab every day. The data is here, here, here. Where you see the blobs, that's the data. But it's over a time period of 2 years. And if you look at the trajectories, these are the trajectories the monkey makes in order to reach each one of the targets. These are the x and y components of the velocity profile of the cursor on the screen. And you can see how, as you go from day 1 to day 400 to day 700, you can see how stable these plots out. And if you actually look at the correlation coefficients between these signals, for instance, on hand velocity, you see that the correlation coefficient, this is hand speed actually, the correlation coefficients are clustered very, very close to 1. So this is a remarkably steady behavioral outcome, which is the same as you do, if you are a pianist or if you play an instrument and you keep on practicing, you acquire a very remarkable stable output. Or if you're an athlete, and you keep on practicing your tennis serves, you acquire a style and you tend to serve. I'm always very impressed when I watch Nadal serving. He has such a distinct way of serving, and it's always the same. It's always, totally the same. So now they practice, whatever, but they maintain this very stable behavior. So the question we asked ourselves was, is there a neural correlate of that? Is there a neural representation of the task that is as stable as the behavior is, and that is maintained over such a long period of time? And so then we said, okay, well, let's look at the neural variability. So here is another monkey that we recorded over a shorter period of time. And here we are comparing the neurons on day 27 with the neurons on day 43. So one of the problems is that these electrode arrays move a little bit over time. Some of them acquire scar tissue around it, so there are some electrodes that you lose. Some of them move closer to a neuron, and suddenly there's a neuron that pops up that you were not recording from before. So you're not always recording from exactly the same neurons. And that's a problem of the technique that needs to be overcome, because if I'm not always recording from the same neurons, it's very hard to ask whether the neural representation is stable or not. And I'll show you how exactly we were able to overcome that. So here, if you look at the number of matched neurons as you increase the number of days between sessions, so this is where that comparison is, neuron 27 compared to neuron 43. So you lose a lot of neurons, even on a scale of a week. There is a constant turnover of the neurons recorded by these multi-electrode arrays. Other techniques might be more stable, but the multi-electrode arrays are really very, very prone to this problem. So this is the question that we ask ourselves. If the behavior is very consistent, is there a neural dynamics that is also very stable and very consistent, and it's underlying this very consistent behavior? And so what's the problem? So the subjects always do the same thing over days, months, and years. We assume that the latent dynamics associated with this consistent behavior should be stable, but we cannot record the same neurons over such a long period of time. So how are we going to verify this hypothesis? In some sense, we need to compensate for the fact that the neurons that are being recorded from are not the same on day n than on day m. Right? And so this is what we were able to do, and what I think is is totally amazing is that we were able to do it completely with linear methods. And I want you to think about what this means. So this here is the true neural space. So this is N infinity. This is all the neurons that participate in that task. And in there is some kind of mother manifold, is the manifold that really controls the task, has all the dimensions that it needs in order to control the task. But when I observe it, I don't observe all the neurons. I observe a projection of that on the neurons that I'm recording from. So I observe a given ambient set of dimensions on day n, a different set of dimensions on day m, and the only thing that I can see is the dynamics on the mother manifold and the true manifold projected into this embedding space of day n, or projected on the space on day m. And these spaces don't even have the same axis, right? Because I'm not recording the same neurons. So how am I going to deal with that? And how am I going to compare those recordings? And so we found, and that's what I'll tell you about, a linear method for aligning these dynamics. What we think is, okay, it's the same object. You are just looking at it from different perspectives. You're projecting it on different axes, and there should be a way of aligning it in order to understand that it is the same object. And the reason why we were not very surprised that we were able to get away with the linear method is because the projections themselves are linear. And then what we did is we work with flat subspaces in each one of these empirical neural spaces. So we reduce the dimensionality both in day n and day m by projecting things into a plane. We probably needed more dimensions than the intrinsic dimension because you're looking at a flat embedding surface. We typically, we did our experiments between 10 and 25 dimensions, so by varying that dimensionality to make sure that our results did not depend on that choice. But these dimensionality reductions were also linear, so we have a linear projection followed by a linear dimensionality reduction. This is why we decided that it made sense to look for a linear method to try to align these two different types of trajectory. So I'm going to give you a quick walk through the methods. I already told you this. We need to compensate for that. So the first thing we do is, so we have a data matrix for day n, and we have a data matrix for day m. And what we did is we create a neural dimension that was the union, the neurons recorded on day n, plus the additional neurons recording on day m. So now when I say capital N, that's the total number of neurons. It's the cardinality of the set of the union of these two neurons. And if the neurons that are not recorded on a given day, we just complete that particular row at that particular day with zeros. So, some days you have some zeros somewhere, and other day you'll have some zeros somewhere else. And there will be some neurons that have non-zero in both days because they were recorded on both days. These are the common neurons, okay? So N is the cardinality of the union set of neurons recording on day N and day M. T is the duration of the experiment. Again, this is discrete time. We created beams of size delta. And what we have is this data matrix. Then both data matrices are for dimension N by T. And we do a singular value decomposition on both of them, on day N and on day M. And the only thing that will matter really is what is the distance between these 2 days. Right? This is what we are going to be plotting things about. So what we do is we take these these matrices UN and UM, which are the matrices that give us a basis for the neural space. And what we did is this matrix we pick the first D columns of the matrix UN, and we pick the first D columns of the matrix UM. So we're doing essentially a principal component analysis of the data on day N and the data on day M. So we pick the first D columns of the matrix UN and UM. We call that UN tilde and UM tilde. So this matrix, instead of being N by T, are D by T. And we construct the D by D inner product of UM transpose. They are D by T. They are T by D, sorry. D by T is correct. And so we do the inner product of these matrices, and we do again a singular value decomposition. And this matrix sigma, which is the diagonal part of the singular value decomposition, is a matrix that has the cosines of the principal angles between these two subspaces. So what we have done, so we worried for a long time about how are we going to compute angles between subspaces that live in different spaces. But by doing this union, we created a common space. So both subspaces live in the same union space. Clearly, I mean, they will have, in some cases, very large angles because there are places where they have zero components. And if there were no neurons in common, so that where one of them is non-zero, the other one is zero, and vice versa, then there would be no common directions, and all the angles will be pi over 2. All the directions will be orthogonal, right? So if I say, look, this one is only along this axis because these two axes are 0, and this one is only along the axis because the other two axes are 0, then clearly there is no way to construct angles that are smaller than pi over 2. But there was sufficient overlap, sufficient neurons in common that we could actually do this. We could define this diagonal matrix lambda and obtain the ordered cosines of the principal angles. Which are the two hyperplanes? One is a d-dimensional hyperplane spanned by the leading eigenvectors of the matrix UN, which is the columns of the matrix UN tilde, and the d-dimensional hyperplane spanned by the leading eigenvectors of which are the columns of tilde, where D is now what I call the flat dimension, right? I'm projecting the data using hyperplanes, which I told you at the very beginning is not really what we would like. What we would really like to do is to go down to nonlinear manifolds and be able to compute the intrinsic dimensions. But the fact that we are willing to stay with a coarser description and looking at a low-dimensional flat space that contains, in which the nonlinear manifold is embedded, allows us to do all these linear algebra manipulations that otherwise we would not be able to do. So there is an advantage to staying naive and staying simple in this case. So we can compute the principal angles, and we can compute, this. But that's not the interesting thing. The interesting thing is to now we take the data and we project the data into these two manifolds. So I take the data xn and I project it into this matrix UN, which are the d principal components on the n, and then I take the data xm and I project it into so I get these two projection matrices. So now these data matrices have dimension d by t, where d is the flat dimension, the dimensionality of my flat manifold, and t again is always the duration of the experiment in this discrete time. Okay, so now I have these two subspaces. The data has been projected in these two subspaces, but I maintain the time order of the data. That's very, very important for something that I'm going to tell you later, that I'm doing really a dynamical analysis. I'm not looking at the cloud of points. The data is ordered in time, and I keep that information of the data being ordered in time. And that's very important for what I'm going to do next, which is to do a canonical correlation analysis. And this is really the alignment step. So the alignment step, what it's trying to do is really align the trajectories. And in order to do that, you have to align time 1 with time 1, time 2 with time 2, time 3 with time 3. So if you apply a permutation over time in both of them, you can still do it. But if you scramble one of the trajectories and not the other, then you're fried. You cannot do it, okay? So the method is actually rather simple. You do a QR, you take these two matrices. Remember, these L and Ln and Lm matrices are the data projected into the corresponding subspaces on the n and the m. Everything is d-dimensional now. You do a QR decomposition. So now, the first d columns of Q provide an orthonormal basis for the column vectors of the L matrix. So they provide orthonormal trajectories, right? Every column here now is a trajectory because I have transposed these matrices before doing the QR decomposition. And so I get these Qs, only one for the n and one for the m. I do again an inner product, and I do another singular value decomposition. So by now you're very good at doing singular value decompositions because we've done like 5 or 6 of them. And what you do now is you use this matrix U and V that you get from the singular value decomposition. You say U is the matrix for the n, and V is the matrix for the m. And you undo the transformation with R. So those of you who have a physics background, remember these Gram-Schmidt orthogonalization devices, right? So Q is a matrix of orthogonal vectors, and R are the mixing coefficients that make the L matrices non-orthonormal. Okay, and so what we are doing now is we got U and V, which are orthonormal, and we use R inverse, which are the triangular matrices in the QR decomposition, to get these matrix M's. And these matrix M's are what allow us to do the alignment. So these matrix M's now are linear transformations, but they are not rotations. They are not orthonormal transformations. They take the subspace N, in which I had a basis, and the subspace M, in which I had a basis, and they create a new basis that spans the same subspace, both here and here. But these new bases are not simply rotations of the old bases. The angles are changed, the scales are changed, because this is a very general linear transformation, a very general matrix, a non-singular matrix. But the beautiful thing is that because of this singular value decomposition and this maximization of the correlations between the Qs, the Q matrix, Qn and Qm, what you have gotten is the first direction in N and the first direction in M are directions along which, if you project the dynamics along that one dimension, they are maximally correlated. And the second dimension are the next maximally correlated, and the two third dimensions are the next maximally correlated, and so on and so forth. So if you now apply these linear transformations to both your day N data and your day M data, you can actually align it. And it's actually rather beautiful. So this is data. This is for a monkey that we recorded over 45 days. This is data on day 1 and on day 32. This is just neural mode 1, neural mode 2, neural mode 3. So this is a reduction of the original data to its own three-dimensional subspace. This is a reduction of the original data in day 32 to its own three-dimensional subspace. And then we align, we do a linear transformation of this space and a linear transformation of this space with the cost function, or the goal of these linear transformations is to maximize the correlations in the dynamics. And this is what we get. So it's truly beautiful, first of all, because it's aligned, and also because it has unscrambled the data. We have these kind of petals that correspond to each one of the reaching directions. Now, this is a bit different from the early work that I showed you coming from the Chenoy lab that Manish was part of, because in that work, there was 1 point per reach, essentially, and the question was whether you could cluster the different reaches. But here we have a trajectory per reach, right? And it's, of course, average over all reaches in that direction, because that's what happens when you do the PCA, the dimensionality reduction. You are averaging over the whole data set to obtain these principal components. But it's very beautiful, and it shows the organization of the task, and again, it shows the topology, because if you look at the order of the colors, this is the same order on this organization, topological organization. So, if you had tried to correlate trajectories in the morning and evening of the same day, you would get something like the gray curve. It's within means within the same day. If you actually let time pass, these are the correlations that you get, much lower, between day 1 and day 32. But if you correct and do the alignment and then recompute the correlations between the aligned signals, is as good as if you had done it on the same day. So we are really getting the signals to be very, very nicely aligned and very nicely correlated, which is a bit surprising. And this is the data for the monkey that we recorded over 32 days. But we had actually 4 different monkeys for which we had data on area M1. This is the one I just showed you. This is 70 days, this is 500 days, and this is 700 days. This is the monkey that was followed over 2 years. And it's, again, totally amazing that the red blobs are statistically indistinguishable from the gray blobs, which are the same day correlations between 2 different sessions on the same day. And it had decayed like that over time, but if you apply this very simple linear alignment, then you can do this. And I want to tell you about work. I don't want to get the steam out of work that Matt Peric will be reporting soon at the meeting on neural control of movement in Croatia in a couple of months. But he has done the same thing across monkeys, not across days for a given monkey. And the method works. That means that there is listen to this, there is a linear method, not LFATs, no recurrent networks, no deep learning, no complex anything, that allows me to uncover dynamics in one monkey doing a given task, in another monkey doing the same task, different brains, different neurons, no overlap between neurons. I find a subspace of 15 dimensions in each one of those two monkeys, and I can use this linear method to align the dynamics. So there is something very, I'll take your question in a second, there is something very intrinsically fundamental about creating a neural representation in your primary motor cortex for this specific task. And even if my brain is different from yours, if we are learning the same task for this very archetypical, very prototypical, very simple task, I don't want to again, I don't want to say that we play piano sonatas the same way in our neural representation, but for this very stereotypical laboratory task, to me, it's totally amazing that you can align across monkeys. Yes, sir, you had a question.
So you just answered my question, but I repeat it again because I think maybe you have some more thoughts on it. So this could be, again, really a property of the fact that this is a very simple task. I mean, the dimensionality of the task is low. So have you,
okay, sorry.
You can do, I mean, you can also make much more complex tasks, but maybe you can go the other way. You can make it even simpler and then see how the quality of the inference method improves or by when you increase the dimensionality of the task.
Right.
And can you speculate on that?
I expect that if you go simpler, it will work. If you go complex, it's.
No, but I mean, how? Like, does it exponentially decay, become worse, or does
you want me to give you a scaling law? No,
exactly.
You need to talk to Surya Ganguly for that.
Okay,
I mean,
I will.
He's the one who has to be more systematic about analyzing. The beautiful work that Surya Ganguly has done is trying to understand how do I assign a number to the dimensionality of a task. And then can I ask whether the dimensionality of the neural manifold that I need to control that task is proportional or similar or at least monotonically related to the dimensionality of the task. But it's really, I mean, the exciting thing about this field is that we know much more than we knew 5 years ago, but there are so many open problems and so many good things to work on, and that's one of them, okay? It's to try to understand how to define dimensionality in task space, So here we have what I call neural modes, right? And what I'm arguing is that the description of the manifold, which is these combinations of neurons, if the manifold is flat, it's just every mode is just a principal component, and a principal component is a linear combination of neurons. It's a direction in neural space in which neurons are activated in fixed proportions, and you could activate that mode more or less. That's the latent activity of that mode, but it's always in the same proportion. It's always in the same direction in neural space. So you have neural modes. We have muscle modes, muscles that we activate also in this. And then some people are beginning to look at behavioral modes in very simple cases for C. elegans, for flies. And so my hypothesis, or my speculation, I should say, is that we should really not think of maps from neural activity to behavior, but we should think of maps from neural modes to muscle modes to behavioral modes, every one of them being in its appropriate low-dimensional representation. And we are much more likely to understand those maps and those transformations if we restrict ourselves to the appropriate low-dimensional spaces, as opposed to trying to look at the space of 10,000 neurons that I can record simultaneously. Okay? You had a question, Tatiana.
Curious if you ever thought about applying those on, let's say, if you take a recurrent neural network and train it to do that. A recurrent neural network, which you train to do the task, and you train multiple of those networks, and they might look different. Like
we haven't, but that's part of the work that has been done. I think Jonathan alluded to that in the group of Mark Chertland and John Cunningham. When they created recurrent neural networks that were able to generate not the kinematics of this task, but the muscle patterns that are related to this kind of very simple reaching tasks, they found these low-dimensional rotational dynamics in the recurrent neural network. So their characterization of the low-dimensional dynamics in the real neural recordings was found, the same features were found in a recurrent neural network that was trained to reproduce the muscles. So, but we haven't looked for that in neural network models because, well, we can talk about it later. I have some reservations about recurrent neural networks. I think they're very difficult to train and very difficult to interpret. And the ones that are easier to train and easier to interpret, which are the layer networks, don't have any feedback, so they are really not very good models for how neurons interact in the brain. So let me tell you one more thing about this, because I want to tell you another couple of things. So it has to do with this transformation from how can we extract information from these signals? So one of the things that you want to do is you want to be able to predict the kinematics. For instance, I want to be able to predict these x and y components of the velocity whenever I do one of these reaching movements to each one of the targets. So each one of these is to one of the different eight targets. And if you train a very simple decoder, a decoder that looks into M1 activity, a linear model, and predicts not the direction of motion, but actually the x and y components of the velocity. And if you train the decoder on the morning and test it in the evening, you get the gray curve. That's the performance, the accuracy of the decoder. If you train the decoder on day one, and you keep on using the same decoder, that's how your performance deteriorates. But if you align the data before feeding it to the decoder, and you can keep on using the same decoder. So why is this very interesting? Because we work with a lot of people who want to use these methods for guiding prosthetic devices. So if every day I have to retrain the decoder, you can do it. I mean, you know, I tell you, get up in the morning and for 15 minutes do the center out task. And that gives me data to retrain the decoder, and that's your decoder for today. But every day is a different decoder. So it's like every day you rent a different car, right? And every day you have to figure out where are the various commands for that car. You have to adapt yourself to using the decoder. Well, if you always use the same decoder, it really becomes an extension of yourself to guide this external device. And so it's very useful to have just a module that you can put in between the neural activity and the input, transform the actual neural activity before you send it as an input to the decoder, and be able to use the same decoder. And so we are able to do that. And
Sarah?
Did I show you the same?
Sarah?
Yes.
I'm a little confused by that. Because don't you need some center-out rehearsal in order to do the alignment?
You need to?
Don't you need some center-out rehearsal in order to do the alignment as well?
I do.
Right, you need some recording under some controlled condition in order to have activity that you can do the alignment with.
I do. Thank you. Now I understand your question. Sorry. Yes, but actually I understand. But it's much less data that I need to retrain a decoder. Now I understand your question. Yep. So instead of half an hour of data, I need like 5 minutes of data in order to do the alignment. Thank you. That's a very good point. So essentially we can do this, and the reason why we can do this is because there is this very lucky combination of linear things that allow us to do this in a linear regime. Again, this is data taken in the Miller lab. Rahid Chowdhury was part of the data taken team together with Matt and Juan, but Juan and Matt and me were the data analysis. And I have to tell you, I've been working for so many years, and I never had such a fun collaboration as I had with Juan Gallego and Matt Parrish. They are amazing people to work with. Now, this paper just came out in January, and we had posted it in the archive it took a year and a half. And the reason why it took a year and a half is because we had referees that believed that Georgopoulos in 1982 suggested cosine tuning for the direction of motion, and that everything should be explained in the basis of these tuning curves. And we were creating this very complicated population code and manifolds, and who knows what manifolds are, and when you should try this way. And I mean, we did like 75 simulations, and one of the referees was, no, you cannot publish this, it's all nonsense. And finally he made a mistake. I say he because most likely, no? I say he. He made a mistake, and he said the definitive simulation would be, and so we did that quote unquote definitive simulation, and we showed once more, like we had done already 74 times, that the Georgopoulos idea explains part of the stability, but it cannot fully explain the stability that we observe with our method. But because he had said this is the definitive one, then he couldn't ask for more. And so he had to let it go. So finally it got published, which reminded me of a very nice quote from Max Planck, which is because here in this group, you don't need that. We all think of population activity. We all think of low-dimensional manifolds and this. And to us, it's very normal to think that way. But there is an old guard out there who really doesn't want you to think that way because they spend their whole lives recording single neurons, and they think that this is the building block. And so according to Max Planck, we just have to wait until they die. This is the only possibility of really affecting a fundamental transformation in the field, because some people seem to be very keen on their vested idea. One of the nice things about being a theorist is you end up working on many different things. So your reputation or your life is not associated with one single idea. So I think that makes you more flexible, because today you're working on this, tomorrow you're working on that. And you don't feel that if one of these ideas is challenged, it's a challenge to your own essence of being. So you are not so stubborn. I want to finish. I have 10 more minutes. I want to show you a couple of things that have nothing to do with our work, but I think it's just totally lovely examples. One of these is this idea of communication subspaces. And again, I was very interested in getting Ken's ideas on this, because Ken has been analyzing data on V1, and this is beautiful work in which they look at how V1 affects V2. So if you do linear dimensionality reduction on V1, like using principal component analysis, what you're looking is you're finding dimensions in V1 that account for the most variance in the activity of V1. But I could ask a different question. I could ask, if I am a neuron in V2 looking at the population activity in V1, which are the directions in V1 that are most relevant to make me fire, to activate me as a V2 neuron? And this defines a subspace in V1, which is not the same as the subspace that you would get if you did an unsupervised principal component analysis in V1, because it's not about variance in V1, it's about how V1 drives V2. So this is totally different, totally beautiful work. And they say, well, what happens if I do dimensionality reduction? Do I find a subspace that is included in the principal component subspace of V1? Do I find a completely different subspace? And so they have this lovely idea of what they call communication subspaces. So they did this dimensionality reduction, again, principal component analysis. This is a talk about everything that you can do with linear methods before you go nonlinear. And what they found is that there is a difference. So there are directions that are the directions of maximally variance in V1, but then there is a subspace in V1, which is the one that maximally drives V2. So they have this idea of selective communication. So there is a subspace which is the communication subspace for area 2, and then there is a lot of activity in V1 that if you activate those directions, you are not communicated to V2. So that means that when you go to V1 and you ask yourself how V1 drives V2, you have to look at the particular neural modes in V1 that are most efficient in driving V2. And there are directions in V1 that will be in the null subspace from that point of view of the communication subspace. And therefore, they refer to activity that goes on in V1 that is not only to drive V2, which we know, I mean, it's expected, right? Because we know that the brain is not a feed-forward system. It's not that V1 is there just to drive V2. There is a lot of recurrent activity, there is feedback, there is a lot of things that V1 is processing, in addition to creating the right signals to drive V2. But those signals had to go through a particular subspace, to a particular communication channel. So I strongly recommend this paper. I think it's a really beautiful example that we cannot interpret activity in V1 only on the basis of how you are stimulating V1, but you have to also ask yourself, how is it driving subsequent areas? And this is again about doing this selective communication and trying to interpret in a neural network manner. Again, a very simple neural network. You should just read the paper. It's a beautiful paper. And finally, I want to say something about nonlinear dimensionality reduction. So we were asking, all this method that I showed you, canonical correlations, really requires following the dynamics. And we thought, well, why can't I look just at the cloud of points and and look at the statistics of that cloud of points and do an alignment based on that alone. And we couldn't do it linearly, and we said, okay, let's try some nonlinear methods. So we tried these autoencoder networks in which you create your spikes, you smooth the spike activity to create firing rates. You have an encoder network that creates a bottleneck. So you put as many dimensions here as you would keep in your PCA, between 10 and 25. These are combinations of the input variables, but they are not linear combinations because they have gone through these several layers of a layer network, which every layer implements a linear combination plus a nonlinear, typically sigmoidal transformation. Then you undo your transformation and you try to reconstruct the firing rates. So if these layers were not there, this would be equivalent to doing PCA, essentially. If this is a linear combination of this, and this is a linear reconstruction of that, and you ask to minimize the square error between the reconstructed signals and the input signals, you would be getting principal components. Not exactly the principal components that you get in principal component analysis, but you'd get 10 vectors, for instance, that span the same subspace as the 10 leading principal components, because that's the way you minimize the variance, that's the way you minimize the reconstruction error. Not to say that each one of them corresponds to principal component 1 or eigenvector 1, eigenvector, that's not the correspondence, but it's something that Jonathan alluded also to. You span the same subspace, it doesn't matter that the basis is not even orthonormal. You just span the same stuff. And then from the latent space, you can use the latent space to do predictions. You can do predictions about the kinematics or predictions about the muscles. So if you want to put that into the autoencoder, now the process at the top is purely unsupervised. Right? It's like doing principal component analysis. If you add this as a part of the way you train the network, then there is a supervised thing. You're also looking for low-dimensional variables that are optimal at reconstructing not just optimally at reconstructing themselves in the unsupervised sense, but optimal at providing input to a decoder that predicts muscle activity based on the neural activity, based on the latent neural activity, based on the latent signals of the neural activity. And I want to finish by showing you something. Instead of doing, we did many things with nonlinear. One of the things that we did was use isomap. And this, I think, is a very nice example of, isomap is another method for nonlinear dimensionality reduction. And this is essentially the eigenvalues. These are the eigenvalues that you get when you do PCA. You see they decrease very, very slowly. There is no obvious place where to put any, obvious place where to cut how many eigenvectors you're going to keep or not. It's a very slow decay, and it's a kind of decay that Ken will tell you about on Friday. This is the kind of decay that he has found in the V1 activity. But this doesn't mean that there isn't an intrinsic dimension, because when you look for a nonlinear manifold and you use isomap, for instance, to find it, you find two leading eigenvalues, and then all these eigenvalues are essentially identical, which is like, say, it's like a coin, like an ellipsoidal coin that has two leading dimensions, and then it has a very small thickness in all the other dimensions in the space. And that thickness is essentially the fluctuation, is the width of the noise. It's the fact that you're not strictly confined to a two-dimensional plane, but you have fluctuations out of that plane, but almost of the same amplitude in all the other dimensions. And here, you can very easily identify that you need to keep two directions, and there is a two-dimensional intrinsic two-dimensional manifold, a manifold whose intrinsic dimension is 2, which you can embed in a flat space, but the dimensionality of the flat space is not a good indication of the dimensionality of the underlying nonlinear manifold. It's not a good indication of the intrinsic dimensionality. And I'm just going to finish by mentioning a beautiful paper also by Brade and Bialek, who hasn't received that much attention and hasn't even been published. It's been in the archive since 2016, in which they argue that instead of looking for a knee here, you should think like in renormalization group, if you're a physicist, and think about what happens as you threshold at different, they argue that these are different resolutions, and to do a renormalization group calculation that tell you how things scale along this axis. And you see that the power law behavior for the slow decay of the eigenvalues that Ken will show you on Friday lends itself very nicely to that idea of, instead of looking for a need that is not there, to say, well, let me think of it as a truly continuous slow decay and study how things evolve, how things scale as I vary where I put the threshold. Instead of looking for a threshold that the linear dimensionality reduction cannot give you, because it's giving you a very large subspace in which the interesting structure is embedded. And to find that interesting structure, you need methods like the one Jonathan talked about, like the one Ila Fite has been developing. I think Manish will also talk about methods that go in that direction. So my talk was not to advertise any of those methods, which are much more complex than what we have done, but just to show you how interesting it is to push the linear ideas as much as you can and learn from them as much as you can, because you'll find real surprises, like, for instance, being able to align brains from different monkeys doing this very simple task. And I'll finish, but I'll show you one slide that goes into the direction of what Yasser was asking. Is this all an artifact of doing a very simple task? So what you would like to do is to have a monkey in its habitat, be able to record it 24 hours a day, getting those signals. The behavior at times could be very simple, at times could be very complex. Follow those signals, try to do the same kind of segmentation according to the videos, what the monkey is doing, trying to do the dimensionality reduction for the different tasks, and see if you can begin to answer these questions of to which extent do these things hold as principles when we allow the behavior to become much more complex than in this very simple centered out task, which is the one that we have used so far. This is a very stereotyped. The monkeys are overtrained. This is why the behavior is so stable. But the idea that I would like to leave you with is, whenever you learn a motor task, particularly one that you practice, be it a sport or music, you create a manifold for that task. And that manifold is low dimensional compared to the 10 to the 6 neurons or even more in your primary motor cortex. And so you have this wiggly surface for one task and another wiggly surface there for another task and another wiggly surface for another task. It's very easy to solve interference problem with this structure. All these wiggly surfaces, manifolds, are low dimensional. They are limited in extent, not only low in dimensional, but what Byron, you and other people call the repertoire. So the extent to which you move out, even within that manifold, is also limited. So these structures sort of interfere with each other, and you can put many of them there, and you can maintain them by practice. And the interesting thing is that when you have two tasks, and that's another paper that we published last year in Nature Communications, when you have two tasks that are in some sense similar, so that the orientation between these planes have some elements in common, that facilitates learning, because there are some modes that you have acquired that can be used to relearn, to learn a task partly within the same manifold. And the only thing that you have to really learn is the directions that are out of the original manifold. And there is beautiful work coming out of Batista's lab that has shown precisely that if you force learning within the manifold, it's very easy, but if you force learning out of the manifold, then you have to acquire new modes, new patterns of activity, and that is a much more difficult learning task for the monkey or for the person, for the organism in general. So I'll stop there. Thank you.
There's one question from the audience.
Yeah, Arvin has a question.
Are there any other questions?
Arvin has a question.
Behavior. I was just curious, like, are there these task manifolds which are different from, let's say, the manifolds in the ongoing activity?
That different from the
ongoing activity, like when monkey. So I guess here the monkey comes in the experimental chamber, and then he knows that he has to work to get the juice and so on.
Yeah, it's very stereotyped.
Exactly, but let's say once they are done and they are relaxing, so how fast this manifold decays into something non-specific,
you transition, and then the question is a question of initialization, and there is very interesting work also coming from the Churchill lab and other labs right now, which is what puts you in the right region of the neural space. So learning has constructed the manifold, but now somebody has to tell you, go to that manifold and
which
use
one
that
to choose from,
manifold for the next activity. So there has to be an initialization that is due to attention, due to sensory input, due to some decision making that the animal says, oh, I'm now going to scratch the back of my head. Something that triggers M1 to go to the correct location. So I was just mostly talking about the acquisition of these manifolds, but then what is the control signals that take you from one manifold to the next, that to associated with transitions in behavior. So as I said, there are many open questions. Yeah. The main open question from the point of view of dynamical systems is what creates these low-dimensional dynamics. So you have a system with millions of neurons, all interconnected, but the dynamics only explores a low-dimensional manifold within this very high-dimensional configuration space or neural space. Why? It has to have to do with the connectivity of the network, but we don't have, I can say that and wave my hands, but that's very different from having a solid theory of what causes these low-dimensional structures to emerge.
Thank you.
I have two questions. Like the first is quite technical. You said that in order to merge or to do this alignment, you first select, you make this one space where you fill in the zeros for the different sessions.
Yes.
Like how is this selected if a neuron is kind of present also in the session, or if it's not present?
There are methods for tracking the identity of the neurons. So this is a slide that I showed you early on, how many neurons you are losing over time. And these methods are based on the shape of the action potential, on the statistics of the interspike interval. So you can say, is this neuron that I'm seeing on day 23 the same as the neuron that electrode is catching on day 46 or not? And if the statistics, the firing statistics of the shape of the action potential have changed dramatically, then you assume it's not the same neuron.
Okay, and then a follow-up question on this, like.
Again?
But how does it work across monkeys? How does it work across monkeys?
How does it work?
Yeah, it's always
Across
zero.
monkeys. It's all because
Yeah.
you said like.
That's true.
Yeah, so across monkeys, you assume there is no intersection. So all the angles are going to be pi over 2. Because
But
you
you
cannot
can
find
still
common neurons, but you can still try to do it. So
correlate.
this subspace and this subspace will have no directions in common because they have no axes in common in the neural space, but you can still do a linear transformation in this subspace and a linear transformation in this subspace to align the dynamics. And that was a complete surprise to us that you could do it.
Yeah.
Actually, people were asking me, what about stitching across monkeys? And I was saying, are you crazy? I mean, I'm not trying to create a little, I'm not Dr. Frankenstein with his assistant Igor trying to create a mirage a chimera of two monkeys. But Matt I just refused to do it. I thought it was crazy. But Matt Parrish was courageous and he did it and it worked.
So it's based on canonical correlation.
He did with canonical correlations. You had
Yeah, I
another
just
question, yes.
exactly because I wanted to know your opinion on imagine you could really record the same neurons over all this time.
Yeah.
Would you expect to not need for the alignment? So would you expect them to be stable, or do you more think of this low-dimensional manifold as something floating?
I would say that it's not the neurons that need to be stable, but it's the manifold that needs to be stable. So if the neurons are changing in such a way that preserves the subspace, it's not that it's inflexible, that the neurons cannot change, but if they change in such a manner that the manifold is invariant under those changes. So there is a lot of discussion about neuronal drift and whether this is against this idea of stable manifolds, and I think it's compatible. So there can be neuronal drift as long as it's consistent with preserving the manifold. Is that your question? Did I answer your question? Tatiana.
I don't believe in decoders anyway, but it would mean that decoder should also drift consistently with the change of.
Should also be?
It should also drift consistently with the change of the manifold.
Yeah, sorry.
This idea that manifold drifts over days would require that the
require
readout
an adjustment of the decoder. Yeah.
Yeah.
Yeah. Yeah. If you
I
cannot,
mean, in the
if
brain.
you cannot compensate for that drift in any simple manner, then you need to adjust the decoder all the time. I agree with you.
Then entire brain has to drift in some consistent.
Yeah.
There's a nice story from
Yeah.
Timothy O'Leary about this.
Yeah.
Why? No, it doesn't have to.
Say it again.
No, it doesn't have to.
Well, if there is a drift.
No, suppose you have a two-dimensional manifold
Yeah.
that you know, and all that matters is the angle between two things, and then the manifold is drifting, and you have a reader who just sums
Well,
and thresholds this. So then it doesn't have to.
So it depends on how. Yeah. So it depends
It
on
really
what
depends
are
on the manifold and what is the movement on that manifold. It could perfectly be
depends-
that the manifold drifts, but it's the decoder could just stay the same.
I understand what you're saying. So it depends on more in detail in the features, in the characteristics of the decoder. But I see the possibility that you're describing. Yeah.
So I will pose two questions from the online
I don't know who hears
audience.
you with this microphone, but I don't.
Stand
Is it
up.
on? Maybe
the
he
same.
hears.
So people online are asking whether you think that these results will also hold for other species such as humans, and whether the method still works if you have highly correlated signals in different channels. These are questions from the
These
audience.
channels are 400 microns away, so the signals are only correlated by the task. They are not correlated, they are independent once conditioned on the task. It's a little bit like the kind of assumptions that Jonathan was making in his model, So once you condition on the appropriate things, then you can assume they are independent. So they are correlations, but they are induced by the task. They are not correlations because these neurons are tightly coupled together. But then again, that's the assumption that goes into the analysis. Whether this assumption is correct or not, that's an important piece of the analysis. And as I said, there is many things that we understand now that we didn't understand 5 years ago, but it is what is exciting about this meeting that we're having and the questions that we're asking is that there are so many things that for which we don't know the answer precisely yet.
Thanks.
That's it.
Okay, thanks.
Thank you.